Okay, now let us begin. So chapter 3, electrical conduction. So previously we have seen how a charge is working. Okay, and now what is the charge, what is the mass, what's the values of the charge in proton and electron and so on. Now today we're going to look at electrical conductions. We're going to see how it flows now in the circuit. Okay, so we have seen how a capacitor works. And we have seen what is a charge. Now we want to focus on the movement of a charge in the circuit, right? So previously we have seen a little bit on how it works. In terms of what is a current, the current, it depends on the speed of charge and so on, right? So today we're going to go into a more details on how it works and what happens when you connect it to a different component. So electrical conduction in a metal. So we are going to focus on metals, how it moves in a metals. So that is what in our syllabus. We're not going to look at the superconductor and so on. Okay, those are not in our syllabus. Our syllabus right now is just electrical conductions in metal. So in metals, the charge carrier is free electron. The things that can move in the metals, that is can move freely, is electron. Okay, we don't have all the other charge particles. Well, it's not that we don't have, but we ignore it. Okay, we ignore all the other charge particles. What we're going to look at is the free electron. Okay, that is our main focus, and that is the major components in the metals. So the charge carrier is a free electron, and there are plenty of free electrons in it. So they move freely and randomly. Now, this is very important. Before you apply electric field across the metals, okay, or the wire, we say it, all these electrons, they move freely and randomly, means that they have no free direction, no fixed direction. Okay, so if you look at this diagram, now it says zigzag motions. So basically it tells you it moves in random. Okay, it can go forward, it can go backwards, it can go up, it can go down. Why? Because when it moves, it keeps colliding with all the other particles. It collides with the holes, the protons in the metals. All right. So zigzag motions, that is just a form of the motion, the description, but the more precise way to describe it is that the charge, it moves freely and randomly. So when you sketch the diagram, okay, if the questions ask you to sketch the motions of a charge in a circuit before you apply the potential difference across it, before you apply the electric field across it, then this is what you should draw, right? You draw a conductor or just a cylinder-shaped tube, then you draw the electron and then a zigzag motions, okay, just a few lines. And those lines, they are not aligned towards the same direction. Okay, they move freely, they move in all directions. So when a conductor is connected to a power supply, a potential difference is applied across the conductor, and therefore electric field is set up in the conductor. So when you have potential difference applied across it, then what happens? This is what happens. Okay, this is when you have V. Okay, this one no V. So when you have a V being applied across the conductor, the freely moved electron will now move in the direction opposing the directions of electric field. Okay, oppose the directions of electric field. Why? This is what I told you before. If you have electric field, for example, now, okay, if you look at this diagram, electric field is going, okay, directions of current is going to the right. Okay, now this is directions of electric field. So we have an electric field that looks like this. Okay, for example, now it means that there is a hidden plate on both sides. Okay, kalau kita ada electric field yang ke kanan, meaning that actually there are two hidden plates that we cannot see. Okay, two hidden terminals that we cannot see. What we do know is when you have electric field, directions of the electric field is always from positive to negative, meaning that the one located on the left-hand side is a positive plate, and then the one located on the right-hand side is a negative plate. That is the reasons why the motions of electron is opposed. Okay, opposing is moving, opposing in the direction opposing the electric field is the opposite direction to the electric field. Because if you have electron, this electron will be attracted towards positive plate. Okay, this is a negative charge. So you have a negative charge and a positive plate, they will attract. And when it comes to electric field is flowing from a positive plate towards negative plate. That's why if you look at the directions of field and the directions of the charge, they are opposed to each other. All right, that is because if you're looking at electric field, actually there are two hidden terminals. Okay, one positive and one negative. How do we know where is positive and where is negative? You look at the directions of electric field. Okay, and from there you will know why electron is moving in the opposite direction. That is because it is being attracted by the positive plate. So with a drift velocity across a cross-sectional area A in times t, drift velocity is known as the average velocity of the free moving electron in the electric field. Okay, so now you have a wire. Okay, wire usually we use a cylindrical shape to represent it. So now what happened is, okay, when it comes to the drift velocity, you look at what happens, okay, in a given times across this given surface area, okay, the red color area. So you look at the times. So the drift velocity can be calculated by using formula Vd equals to I over NAE. Okay, where your Vd represents drift velocity, I is the current, the values, the magnitudes of current. Small letter n is the numbers of free electron per unit volume. A is the cross-sectional area. E is the charge of electron. Okay, now this E is the elementary charge, but since we are looking at the conductor, we are looking at the electron flow. Therefore, this E can also be known as the charge of electron. But when it comes to the list of constant in your exam, E is actually represent charge of elementary particles, okay, elementary charge. Okay, now these equations, if I'm not mistaken, is not in your syllabus. So we give you this equation just as an additional info for you to understand what is the velocity. It depends on what? It depends on the current. Okay, if you have a larger current, then means that you have a higher velocity. If you have a larger surface area, then a smaller velocity, and so on. All right, so this is just to tell you the relationship between V, I, N, A, and E. That's it. All right, so just an additional info. You don't have to memorize these equations. So in a circuit, electrons actually flow through the metal's wire. However, it is customary that to use a conventional current to describe the flow of charge. So in our wire, okay, when it comes to a circuit, when we draw a circuit diagram, we don't draw it according to the directions of current of the electron flow. We draw it according to the directions of current flow. Okay, that is the meaning of this sentence. So we use current to describe the flows of a charge. The directions of conventional current is always from higher potential towards the points of lower potential. So current is being pushed from higher potentials to lower potentials. So what exactly is current? Now, current is defined as amounts of charge per unit time. So you have the imaginary surface here. You want to look at it in a given times, how many charge passes through this given surface area, okay, given imaginary surface. So mathematically, I is equals to, is equals to what? Now, because we're looking at the numbers of charge passes through this surface area over a given amount of time. So I is equals to dq over dt. Okay, so Q represents the charge carried by the free electron, and then T is the time taken for it to move through this imaginary surface. So we look at how many charge passes through this surface area in a given time. So that would be our current. Okay, so if you have more charge can pass through this surface area, okay, or at a given times, then you have a larger I, okay, greater current. So current is a base quantity and it is also a scalar quantity. Okay, it is a base quantity and it is also a scalar quantity. So the base unit for current is ampere. So ampere is also an SI unit. Now, what does it mean by ampere? 1 ampere is defined as 1 coulomb of charge passes through the surface area in 1 second. So 1 ampere is equals to 1 coulomb over 1 second. Okay, 1 second. So it is also equals to 1 CS negative 1. Okay, so 1 ampere, the unit can also be written as CS negative 1. Coulomb per second. How many coulombs of charge passes through the given surface area per 1 second? That is the meaning of ampere. So if you have 10 ampere, it means now there are 10 coulombs of charge passes through the surface area in 1 second, okay, the given surface area. So that is the meaning of current. So Ohm's law, okay, Ohm's law, it states that the potential difference across a metallic conductor is proportional to the current flowing through it if the temperature is constant. Now, when it comes to Ohm's law, it tells you the relationship between I and V now. Just now, we say current is flowing from higher potential towards lower potential. Okay, now we want to see in terms of a mathematics aspect. Okay, what is the relationship between V and I? Okay, mathematically. So the potential difference across a metallic conductor is proportional to the current flow. V is directly proportional to I. So if you have a larger potential difference, then larger I. Why I is larger when there's higher potential difference? Because your electron can flow faster. Okay, like what I told you in the previous chapter, the reasons why an electron can flow is because there's a potential difference. Okay, for example, this is the plate and this is the power supply. Okay, let's draw it like this. Okay, so this is a plate and then, oops. Okay, and then you have a power supply. The reasons why electron can flow, that is because initially your capacitor is neutral. So V is 0. So power supply, let's say now you have 10 volt. So there is a potential difference between capacitor and the power supply. Therefore, your electron can flow. And initially, it can flow very fast. Why? Because the difference between the potentials of the battery and the capacitor is at its largest value. Okay? So electron can flow faster. When electron flow faster, okay, electron flows faster, then it means you have larger current, larger I. Why? Because I is equals to dq over dt. More charge can pass through the given area over maybe 1 second. All right, so this is your cable. Let's say this is your wire. So now this is the surface area, your imaginary surface area, the surface area they're looking at. So if they can flow faster, then every second, definitely you have more electron passes through this surface area. That's why you have a larger I. Okay, so V is directly proportional to I. Provided if temperature is constant, if you're going to look at Ohm's law, okay, the condition for Ohm's law to be valid. If temperature is not constant, then it doesn't obey Ohm's law. Okay, if you have a scenario, a case where temperature is not constant, then you cannot say the Ohm's law is valid in that situation. It is invalid. Okay, it is invalid if you are not controlling temperature, if you are not making sure that the temperature is constant. So in order for Ohm's law to be valid, okay, temperature must be kept constant. So V is directly proportional to I. That is the relationship. So to make it into a mathematical equations, so V is equals to IR. We add a constant, and the constant in this equation, we call it resistance. Okay, so the constant in this equation is a resistance, meaning that if you're using the same resistor, then the values of R would be fixed. So by changing the I or the V, it won't change the values of resistor. Okay, so isn't it very familiar, this statement? Because in chapter 2, where you have a C equals to Q over V, when it comes to this equation, okay, Q depends on V. You change Q, you change V. C is kept constant. Now, in this case, in this chapter, Same things happen. If you change I, you change the V, but R is constant. So resistor and capacitor, actually they are very similar in terms of the idea, of the concept, in terms of the equation, all right? So equation for capacitor is C equals to Q over V, but when it comes to this equation, okay, Q and V, it doesn't affect the values of C. Okay, if you change Q, you change the V. If you change V, you're changing the Q. C is kept constant. When it comes to chapter 3, V is equals to IR. If you change I, you change the V. If you change V, then I changes. It won't affect the values of R. R is kept constant in this case. So R is equals to V over I. So even the equation, they looks very similar, right? So they are fraction form. They are looking at the ratio. They represent a ratio. Just as R is the ratio of a V to I, C is the ratios of Q to V. Okay, so in terms of formula, they are very similar. In terms of idea, they are also very similar. They are not being affected by the potential difference. They are not being affected by the charge, by the current. They are a constant value, provided if you're using the same component. You're not modifying the capacitor, you're not modifying the resistor, then the value would be the same, would be kept constant. Unless you modify it, you change the physical structure of the resistor. Okay, if you change the physical structure of the resistor, if you change the physical structure of the capacitor, then yes, you can change the values of resistance, you can change the values of capacitance. All right, so chapter 2 and chapter 3, when it comes to these electrical components, the resistor and the capacitor, they are very similar. Okay, they have the same idea there. So if you understand how a capacitor works, then it shouldn't be an issue for you to understand how a resistor works, how to calculate the values of a resistance. Okay, so figure below, it shows the linear relationship between V and I for a metals or a conductor. Okay, to be more precise, it's a metal. All right, you're looking at metal. So some conductor, they are not metal. If they are not metals, then you won't have this relationship as well. So this graph is only valid, okay, it shows that it obeys Ohm's law. Okay, it obeys Ohm's law. So material that obeys Ohm's law are material that have a constant resistance over a wide range of potential difference. For example, ohmic conductor, okay, which is a pure metal. Metal that do not obey Ohm's law, they are known as non-ohmic conductor. They are still conductor, but they are non-ohmic conductor. Okay, for example, we have a carbon or a semiconductor or a superconductor and so on. And then V against I, the gradient will give you R. Okay, gradients of a V against I graph, it gives you R. So, okay, so if you compare it again with chapter 2, we have Q against V graph. Q against V graph, the gradient represent capacitance. So tengok, dia punya idea lebih kurang sama tau. Kalau kamu tengok dari segi dia punya equations punya bentuk, kamu tengok dari segi dia punya graph, kamu tengok dari segi dia punya ciri-ciri untuk komponen tersebut, which is constant. If you are using the same component, then the R, the C, they are constant. Then now let's see, what is the things that will affect the values of resistance? Resistance is defined as a ratio. So it's a constant. So it's defined as a ratio of the potential difference across an electrical component to the current passing through it. Mathematically, R is equals to V over I, just a ratio. Okay, just a ratio. It is a measure of the component's opposition to the flows of the electric current. Okay, so the larger the R means that they will oppose the flows of current. Okay, greater opposition. Dia semakin kuat menentang. So the resistance depends on the type of materials, the length, the cross-sectional area, and the temperature of the conductor. So it depends on these few things. The type of material, obviously. If you're using same types of material, then it won't change. If you change the materials, then they will have a different values. Okay, this type of material, it depends on what? It depends on what we call resistivity. So on the right hand side, we will talk about resistivity after this. So in your capacitor, it depends on the material of dielectric. So in a capacitor, in resistor, it depends on the type of material, which is resistivity. Okay, when we talk about a type of material, actually it refers to the resistivity. So, okay, I will just write a capacitor right here, yeah, so that you can see the similarity between resistor and capacitor. So for capacitor, it depends on the type of dielectric. Okay, the types of the types of dielectric. Okay, which is our permittivity, our epsilon. Okay, so the second things, R, it depends on the length. Okay, and then it depends on the cross-sectional area of the wire, length and the cross-sectional area. When it comes to capacitor, it depends on what? Well, it depends on the shape and the size of the plate. Okay, which is the area. And then the third thing, it depends on what? It depends on the distance between plate. Okay, distance between plate. So this depends on D. So in chapter 2, capacitor, it depends on these three things. In chapter 3, resistor, it depends on type of the material, which is resistivity or rho, and then the length L, and the cross-sectional area A. Okay, and the last one, obviously, the temperature must be kept constant. Okay, because we are looking at Ohm's law. So temperature of the conductor will affect the values of resistance as well. We will explain this temperature in the next subtopic. Okay, right now we focus on the first three. First three things, they are the things that will affect your resistance. So it is a scalar quantity and the unit is known as ohm. And because we are looking at the ratio of V over I, therefore it can be written as volt per ampere as well. So resistivity is defined as a resistance of a unit cross-sectional area per unit length of material. Mathematically, rho is equals to RA over L. Okay, so how do we know this one? Well, let us go back to resistance. Resistance, it tells you it depends on the type of material, okay, which means R is directly proportional to rho. The second thing, it tells you it depends on the length. Okay, it depends on the length. Well, to be more precise, we ignore the resistivity first. It depends on the length. So the longer something it is, obviously it's going to experience more resistance, right? Because it's going to take more time to travel from one end to the other end. So R is directly proportional to L, but then R is inversely proportional to A. Inversely. Okay, 1 over A. If you have a larger surface area, obviously it's getting easier to travel through the path, the surface area, the conductor. So R is directly proportional to I, R is that inversely proportional to A. When you combine these two things, it gives you a relationship. R is proportional to L over A. Added in a constant, R is equals to rho L over A. And this rho, it represents the constant, which is the type of material. Okay, so rearrange the equations, it gives you the definitions of resistivity. All right, this is how we obtain the equations. Rho equals to RA over L. Starting from the relationship between R and L, R and A. So R is directly proportional to L. The longer something is, then it's going to facing more opposition. It's harder to travel, to finish traveling the whole thing. And then R is inversely proportional to A. The larger the surface area, easier to move. Okay, experience less resistance. So R is proportional to L over A, added in a constant value. So R equals to rho L over A. And rho is a constant value, which it depends on the type of material. So we call it resistivity. So resistivity is equals to RA over I. It is a measure of material ability, material's ability to oppose the flows of electric current. Therefore, we say it depends on material. So resistivity depends on the type of material and it depends on the temperature. Good conductor have low resistivity. Good insulator, it has high resistivity. So again, it is a scalar quantity and the unit is ohm meter. Okay, bukan ohm ya. Resistivity is ohm meter. Resistance is ohm. Okay, resistivity is ohm meter. So the table shows the resistivity for the materials at a 20 degrees C. Now, 20 degrees C, this is our reference temperature. Okay, reference temperature. So most of the resistivity given on the electrical component, if you go out, you buy something, you buy some electrical component, you buy some materials, the metals, the conductor, okay, the resistivity returns on the what, yeah, on the label. Okay, on the label, actually they record it based on the temperature 20 degrees C. So this is a reference temperature in most of the electrical component. Okay, so semua nilai resistivity, kalau kamu pergi beli conductor, okay, pergi beli alat elektrik, kadang-kadang dia bagi tahu kamu nilai resistivity, dia ada tulis dekat label dia. Nilai-nilai yang diberi ini sebenarnya dia ambil pada suhu 20 degrees C. Okay, so at 20 degrees C, silver has a resistivity, okay, 1.5. Now, okay, all this I will leave it to you lah. Okay, all this you don't have to memorize. Okay, you don't have to memorize. It will be given. Dalam soalan, kalau Anda perlu kira, Anda perlu nilai resistivity, dia akan bagi, so you don't have to memorize any of this value. Here, they just give you a few examples so that you can see. So the one with a smaller resistivity means that it is a better conductor. So obviously, if you look at the the resistivity is 10 to the power of 10 until 10 to the power of 14. Well, maybe it can conduct current, but it is a very, very bad conductor, okay? It's more to insulator because if you look at the power is up to 10 to the power of 10 and 10 to the power of 14. Whereas you look at all the other metal, their power is all -8. Okay, they are all -8. So all these four, the first four, they are conductor. And then the last one is the insulator. The glass is insulator because it opposes the flows of current. Okay, it has such a large resistivity. All right, so we are done. Okay, so we have seen how a charge flow in a metals, and now we've seen what is current. We have investigated the relationship between I and V. Okay, and now we look at the constant value R. So we have seen what is R, and then what is the things that affect R. Okay, and then what is resistivity? Now we want to look at temperature. Just now we said all those values, they are being recorded at 20 degrees C. What if you change the temperature? So this is what is going to happen. So as the temperature across the ohmic conductor increase, resistance also increase, meaning that R is directly proportional to T. Why? Because when the temperature increases, the numbers of free electron per unit volume in the metals remain unchanged. Okay, but okay, let's say now this is your metal. Okay, this is your metal. So inside metals, there are a lot of atoms, right? There are a lot of atoms. Example. Okay, examples. You have a lot of atoms in it. But even if you increase the temperature, okay, let's say now this is the free electron. Initially, you have this amount of free electron. Okay, you have this amount of free electron. Now, when you increase the temperature, the numbers of free electron remain at 5. It won't increase. Okay, numbers of electron, it does not depend on temperature. But what happens when you increase the temperature? Now, you're looking at metals. Inside the metals, there are plenty of atoms. If you increase the temperature, all these atoms, they are going to vibrate with a larger amplitude. Okay, so metal atoms in the crystal lattice, they vibrate with a larger amplitude, the greater amplitude, and causes the numbers of collision between electron and the atom increases. Okay, increase. So maybe initially, okay, if this electron, it want to travel from, let's say, from here, okay, from this position, you want to travel from here to here, okay, let's say you want to travel until the end to the right hand side, maybe it will just collide with this atom, this one atom, okay, it will just collide with one atom. But when you increase the temperature, okay, initially they vibrate at a small amplitude, so it can travel freely, just collide with one atom before it reaches the right end. But if you increase the temperature, now all atoms, they are going to vibrate at a larger amplitude. So maybe it will collide with, let's say, at least three of them. This one, and this one, before it reaches the right-hand side. So that is the meanings of it causes the numbers of collisions increases. Okay, the increase. So initially, maybe it just collide with one, but when they vibrate at a larger amplitude, okay, so what does it mean by vibrate at a larger amplitude? So initially, dia vibrate small saja, sikit saja. If you increase the temperature, dia vibrate begitu besar, okay, it move up and down, the distance increase. So electron collide with more of the atom. So hence, we say resistance increase. Now, why? Okay, why these metal atoms, they can vibrate at a larger amplitude with a greater amplitude? That is because, okay, I want you to add in one sentence. When temperature increase, okay, temperature increase, atoms, they gain more kinetic energy. Okay, atom gains more kinetic energy. Or you can say kinetic energy increase. When temperature increase, kinetic energy increase. Okay, or atoms, they gain more kinetic energy. That is the reasons why they can vibrate with larger amplitude. Okay, so basically you are looking at the relationship between T, you start from temperature increase, okay, followed by, if temperature increase, followed by kinetic energy of the atoms increase. Okay, they gain more kinetic energy. What happens when they gain more kinetic energy? Amplitude increase. Okay, amplitude increase. What does it mean by amplitude increase? More collision. Okay, more collision. So numbers of collisions increase. What does it mean by numbers of collision increase? Well, that means resistance increase. Why? Because it's getting harder for the electron to travel towards the other side. Okay, towards the other end. So basically, this is what happened. You see, from just a one action, okay, you just change the temperature. That is the consequence. You have a consequence followed by temperature increase. So temperature increase, gain more kinetic energy. More kinetic energy leads to larger amplitude. Larger amplitude causes more collision. More collisions, what does it mean? It means now the resistance increase. Therefore, okay, therefore we say R is directly proportional to T based on these two. Okay, R is directly proportional to T. So for many materials and a limited temperature range, it is possible to express the temperature dependence of the resistance as follows. So R is equals to R naught bracket 1 plus alpha delta T. Okay, 1 plus alpha delta T. So delta T, it represents T final minus T initial. Okay, T final minus T initial. The change in temperature. Since the resistivity is given by rho equals to RA over L, both sides of the equations can then be multiplied by A over L. So you can replace R equals to, okay, if you rearrange these equations, you will obtain R equals to rho L over A. You sub rho L over A into the equations above, you will then obtain rho equals to rho naught, the rho initial temperature, bracket 1 plus alpha delta T. Okay, that's why in a previous page, in a page 50, it tells you both R and rho, they depends on temperature. Okay, depends on temperature because of this, okay, because of these two equations. So by using these two equations, you can then find a new temperature, new resistance and new resistivity. Okay, new resistance and new resistivity. Now, sometimes questions will just give you one temperature, then by default, okay, our reference temperature will be 20 degrees C. Okay, kita punya reference temperature is 20 degrees C. So, kalau soalan cuma bagi Anda satu temperature, dan satu lagi, kita boleh anggap dia 20 degrees C. Okay. So, temperature coefficient of resistivity, which is the A, can be defined as fractional. Okay, so basically you just rearrange the equations. You will obtain alpha equals to rho over rho naught delta T. Okay, rho over rho naught delta T. Rho over rho naught delta T. So how to obtain these equations? Basically, you just rearrange it lah. So from here to here, you rearrange the equations. Rho, okay, divided by rho naught equals to 1 plus alpha delta T, I think. Am I right? Yes. Wait, yeah, let me see. Rho over rho naught alpha equals to yeah, you give me a moment. I think the equations got something wrong. Temperature coefficients of resistivity. Yes, okay, the equations should be delta rho. Okay, delta rho. So equations asal dia ada salah. Okay, so delta rho. Why? Because if you expand the equations, okay, rho is equals to rho naught plus rho naught alpha delta T. Rearrange the equations. Rho minus rho naught equals to rho naught alpha delta T. This part can be written as delta rho equals to rho naught alpha delta T. Therefore, alpha is equals to delta rho over rho naught delta T. So this is the definitions of alpha, okay, temperature coefficients of resistivity. So sepatutnya ada satu delta di sini. So alpha equals to delta, the change in resistivity, over delta over rho naught, which is the initial or the resistivity at T naught, okay, and then times with delta T. So the unit of alpha is C -1 or K -1, okay? It's either one. It doesn't matter. Why? Because you are looking at the change in temperature. So change in temperature in Kelvin, again, is same as the change in a temperature in degree C. Okay, ini yang kita sudah pernah tengok di sem lepas. Dia tak kisah kamu tengok degree C atau Kelvin. Okay, sebab apa? Sebab temperature change dalam degree C dengan dalam Kelvin adalah dia sama. Okay, adalah dia sama. Okay, so yeah. Oh yeah, I want you to make a bit of corrections right here. Yeah, G here it should be delta rho. Delta rho over rho naught is a fractional increase in resistivity. Okay, ada delta di sini. Okay, ada delta di sini. So ada typo dalam buku Anda. There should be a delta right here. Okay, there should be a delta. So delta rho over rho naught. And then corrections here, not C -1, but degree C -1. Okay, degree C -1. So buat sedikit correction, ada 2 mistake dalam buku anda. Okay, ada 2 mistake dalam buku anda. Kamu buat sedikit pembetulan. Alright. So this page, I give you a bit of time to write it down. Okay, because this page usually students got a bit of issue with it. Okay, they are having a hard time to understand this part. So basically, you're just looking at here and this one. Okay, this is the main focus. You look at what happens when you change the temperature and the reasons why, and then you have to know the equation. Now in this chapter, actually it's quite simple, you know. Whenever you have a questions with temperature, then these are the only equations that you can use. Okay, these two are the only equations that you can use when it comes to temperature, when you have temperature in the questions, right? So I give you 2 minutes to go through it before we proceed to the next part. Okay, 2 minit bagi Anda sebelum kita proceed ke part yang seterusnya. So kamu boleh buat catatan sikit, terutama yang saya highlight punya yang warna hijau itu. Okay, kamu buat sikit catatan. And then derivations di part ini pun mungkin Anda boleh catat.